Oops. Okay. Oops. Wait lang. Yan. Okay, so last time we discussed fault analysis, what is fault analysis, and then basically what is a fault point, how to get the fault current, and then I introduced you to interpreting three-phase faults, which is symmetrical fault because at the instant of the fault, the system is still balanced. Okay, now what uh, what we're discussing now is how are we going to interpret if how are we going to analyze a system that experienced a fault that is not symmetric? So what does it mean? It means that at the instant of the fault, your system is not balanced. So how will that happen? Suppose let's say that I have this three line three line system. So it's a three phase. So those three line system, that's my three phase line. This is my ground. So I guess for this for this consideration example, I'll just demonstrate shunt fault, grounded shunt fault. Yeah, it's a short circuit fault. So if we consider a three-phase fault, that's basically if your three-phase, all of these three lines are connected to each other. They can be grounded, they can be not grounded. It's basically the same. Okay. So what will happen if instead of, if this is my three lines, this is my ground, instead of all of those three lines are grounded, what if only one line is grounded? So if only one line is grounded, therefore I cannot say that my system is still balanced, because now I have a line that is grounded and then two lines that are not grounded. So I cannot represent this into a single line diagram because I cannot perform per phase analysis. Basically, I cannot perform per phase analysis on an unbalanced system. So you cannot do well, at least for the knowledge that we have right now. We can perform that. So we cannot represent this yet into a single line diagram from the techniques that we did on three phase fault. So basically what we're doing is a new approach. So before we go into these types of fault, let me introduce you into this into Fortescue's theorem. So the idea of Fortescue is that if you have unbalanced phasors like this one, these are three unbalanced phasors. I have A. Sorry, where is A? This is A. I have this A, this B, this is C. So as you can see, A leads B, B leads C. So that this is actually a positive sequence ABC. Okay, so this is a positive sequence ABC system. Unbalanced, they have different magnitudes, not separated by 120 degrees. They can have the same magnitudes, but if they are not separated by 120 degrees, therefore they are still not balanced. Okay. So the idea for test is that if you have an unbalanced system of vectors, these three vectors, this unbalanced system is basically a sum of three balanced systems. So the idea is that if I have this vector A, this is the sum of three A vectors, A1, A2, and A0. I have this B. B is the sum of three vectors, B1, B2, and B0. I have this vector C, which is a sum of three vectors, C1, C2, and C0. So that's basically Fortescue's theorem. And what's with those A1, A2, A0, B1, B2, B0, C1, C2, C0? Those are basically your vector components from your three balance systems, such that A1, B1, and C1 is a balanced system. A2, B2, C2 is a balanced system, and A0, B0, and C0 is a balanced system. So that's basically the the idea. So what's the difference between A0, A2, A1, A2, and A0? Those are what we call positive sequence for A1, negative sequence for A2, and zero sequence for A0. So yeah, so this is basically your A1, B1, and C1. As you can see, this is a balanced system. They are of the same magnitude, all separated by 120 degrees. I have A2, B2, and C2, same magnitude, separated by 120 degrees. And there is a special consideration for zero sequence. The idea of zero sequence is that you have three vectors A0, B0, and C0, all of them same magnitude and at the same direction. Okay, so that's more like an exemption. Okay. Yeah, so how do we characterize the three sequences? So your positive sequence is basically a balanced three-phase, same magnitude, displaced by 120 degrees, but have the same phase sequence as the original phasor. So what does it mean? Take note, from here, from the original unbalanced vector, we know that A leads B, B leads C. A leads B, B leads C. So it's an ABC sequence. A leads B, B leads C, C leads A, and then the cycle goes on. Okay, so it's an ABC sequence. So the positive sequence here, by the way, this is called symmetrical components. These three sequences are called symmetrical components. So the positive sequence symmetrical component is the same phase sequence as the original phasor. So if the original phasor is ABC sequence, therefore the positive sequence symmetrical component is also ABC. That's why in this diagram, you have A1 leading B1, B1 leading C1. So if instead of A leading B, B leading C, I have A, let's say that this is A, and then let's say that this is C, and this is B. Therefore, A leads C, C leads B. So now I have an ACB sequence. So therefore, my positive sequence symmetrical component will also be ACB. So what will happen here is this will be A1, C1, and B1. Okay? Take note again, the original network in this example, the example that I am using, this one, is ABC sequence. That's why the positive sequence is ABC. The positive sequence symmetrical component. Okay? Now, the negative sequence symmetrical component, it's basically it's still a balanced system. You have the same magnitude for each vectors A2, B2, and C2, but they are displaced by 120 degrees, but they are opposite phase sequences the original phasors. So the original phasors, these original phasors are in A, B, C. Therefore, the negative sequence, this one, will be in ACB. So if I zoom this in, I have A leading C, leading B. So it's ACB. Okay. So for the zero sequence is just three phasors equal in magnitudes displaced by 0 degrees. So they are basically in the same direction. Okay, so that's Fortescue theorem. It just tells you that if you have a set of unbalanced vectors, it's just the sum of a three-phase unbalanced. If you have a set of three-phase unbalanced vectors, it's just the sum of three balanced networks, your symmetrical components. So you have the positive sequence, the negative sequence, and the zero sequence symmetrical component. Okay. I have this is actually in your handouts. This is just my PowerPoint slides for your handouts. This is just the representation of how to, this is just the mathematical representation of your Fortescue theorem. You have this unbalanced set of vectors. It's basically the sum of your balance networks. So VA is just the sum of positive, negative, and 0. VB is sum of positive, negative, and 0. VC, positive, negative, and 0 of C. Okay. I have here the derivation of the A matrix. So basically, the A matrix is derived using this one. Yeah. Where is that? This one. Okay. So, for simplicity, we may assume that A is 1 angle 120. It's just a displacement multiplier. So, the idea is that if you represent all of these unbalanced sets into a vector of A's, so you have VA is VA1 plus VA2 and VA0. VB is VB1. And take note, VB1 is 240 degrees from A1, or negative 120 degrees from A1. So that is basically A squared. VB2 is positive 120 degrees from A2, so it's A. Okay, and then VB0 is basically the same. It's basically equal to VA0. So that's how you get this equation. Okay, and then you can represent this in matrix form such that you have this one. So this is your A matrix. Okay, so this is just a way of representing your unbalanced networks into 3 balanced systems, and then how are you going to relate all of them. Okay, so that is your A matrix. Okay, yeah, what I have here, this one. Okay, yeah, okay. Okay, this one. If you have, basically, if you have the original unbalanced network, you can use the A matrix, multiply it by inverse that A matrix to get the symmetrical components A1, A2, and A0. So how do we get B1, B2, B0, C1, C2, C0? Of course, you know that these are balanced systems. So once you know that A1, A2, what are the values of A1, A2, and A0, you can easily get B1, B2, and B0, C1 and C2 and C0 just by displacing it by 120 degrees. Kasi it's a balanced network naman eh. The 3 symmetrical components are balanced networks. Okay, so yeah, what more? I guess, yeah. And then this you call this this one is just also equivalent to this one. This is purely mathematics. You can review this at home. You have your handouts. I won't show the derivation here. I guess what I want you to get from this theorem is that if you encountered an unbalanced system, of course, you cannot represent that into a single line diagram because it's unbalanced. However, you can represent that unbalanced system to 3 different systems. And all of these 3 are balanced systems. Therefore, each of these can be represented into individual single line diagrams. So if you have an unbalanced network, it's basically the sum of 3 balanced networks. So you have 3 single line diagrams. So yeah, that is how we are going to approach unbalanced, unsymmetrical faults. That's our approach in unsymmetrical faults, because unsymmetrical faults causes the system to be unbalanced. So I guess I'll be back with the discussion on different unsymmetrical faults. So yeah.